Now, before solving problems, if I have to ask you what will be the factors which will govern the rate of reaction of SN2 through SN2 mechanism. Governs the rate of reaction means what will be the factors which will increase the rate of reaction, or for that matter decrease the rate of reaction. For example, let's start thinking on certain terminologies. Let's consider the first factor, that is nucleophilicity. Nucleophilicity means the capability of a nucleophile to participate in the reaction. Nucleophilicity means whether the nucleophile is hard nucleophile or a soft nucleophile. Hard means hard. Hard means hard. Hard means hard. Yeah, hard means hard. Hard means very vehemently reacting in the reaction. Will not see anything. It will pour its electron anywhere it finds a empty orbital or empty antibonding or bonding orbital, whatever. So hard means highly unstable. Given a chance, if you drop into the system, it will quickly participate in reaction. It can't remain as it is. So hard nucleophile will be those nucleophiles which are incapable of holding that negative charge owing to less electronegativity and small size. So the hardest nucleophile that will be there will be the negative charge on the smallest atom, that is hydrogen. Hydrogen is small, very small, having electronegativity value very less. So the negative charge on hydrogen would be very unstable. So that makes hydride ion hard nucleophile. Similarly, negative charge on carbon would be a hard nucleophile. In general, we have any alkyl group. Alkyl group means carbon, hydrogen, hydrocarbon. So negative charge on R minus will be a hard nucleophile, right? If negative charge is stable, so suppose we have alkoxide ion. Now oxygen belongs to second period. Size is not big, size is small, but the electronegativity value is very high. Oxygen being the second most electronegative atom, negative charge on oxygen is considerably fairly stable. So this O minus, RO minus will be a moderate, not very soft, but still not a hard nucleophile. This will be a stable ion, making this a not hard nucleophile or a moderate, a nucleophile having moderate nucleophilicity. Similarly, if you have a negative charge on nitrogen, this will be a moderate nucleophile, not hard, right? But if you have Cl minus, this will be a soft nucleophile. These would be hard nucleophile, and this would be having nucleophilicity. Oh, this will be having nucleophilicity of moderate level. So if negative charge is on carbon or hydrogen, that makes it very hard. If negative charge is on more electronegative element, that makes it moderately nucleophile. That makes it have moderate nucleophilicity. If the negative charge is on bigger atom and having more electronegativity, that makes that ion stable and hence a soft nucleophile, not will be doing much of the hindrance, or even if it comes to pour the electron into the antibonding, it will be kicked off. So making this less nucleophilic. So Cl minus ion, Br minus ion, iodide ion, these will be soft nucleophiles. Okay. So if the nucleophilicity increases, then the rate of reaction increases. There will be attack. Say it will attack the substrate, and the rate of reaction will increase, will be very high in case the nucleophilicity is very high. So one of the factors that will govern the rate of reaction will be nucleophilicity. Okay. Next factor that will govern the reaction will be nature of Lg. What is Lg? What is Lg? What is Lg? Lg is leaving group. Remember? Lg is leaving group. Now you must be having a very good picture of what this SN2 reaction is. Someone will come in, pour its electrons, someone has to go off. So if we're having, like, suppose if we have, in previous case we had CS3Cl. But suppose if we had CS3, then what would have happened? Or instead of CS3, any other R group in general, we have any other in general R group. So here what happened, if you're having a nucleophile, we'll be representing nucleophile as Nu minus. If you have a nucleophile, this nucleophile will pour in electron. So the sum of the electronic density will go into the orbital of chlorine. Chlorine moves off. This Nu gets attached to CS3, forming a new compound. Hence a reaction occurs. Clear. But in this case, if we have a similar situation, if you pour in a nucleophile, then the nucleophile will attempt to pour its electron into the empty orbital of CS3. Now CS3 is left with two options. Either it kicks away the nucleophile, not allowing it to pour its electron into the empty orbital of CS3, or it will dole its electron into the orbital of R. But then R have to move out as R minus, and here as CS3 moves out, Cl moves out as Cl minus. R minus is not stable, by the way, and hence R minus will have no motivation to move out. So R minus will be resistant to this kind of reaction, this kind of leaving the substrate. So R minus won't go out. R minus is not ready to go out because R, remember, R is alkyl group. So R is having carbon chain. This negative charge is ultimately on carbon in this R minus. So R minus won't go. If R minus won't go, CS3 can't increase its electronic density more than 2. So if it is not, if it cannot empty up its electron into someone else's orbital, then CS3 won't allow the increment of electronic density into its anti-bonding orbital. So in that case, Nu minus or nucleophile cannot pour its electron. In that case, there will be no reaction because Nu minus cannot put its electron, R minus cannot go out. So this is the second case actually, which I said a moment before we didn't discuss. So if instead of Cl, if we have R group, then there will be no reaction because R group won't go out. You need to have a good leaving group. Good leaving group will be the one which is stable independently, so that it can reside somewhere, move out, and have its independent existence. Cl minus, big in size, high in electronegativity value, is stable. R minus, carbon being less electronegative and having lesser size, will not be stable. So this reaction will be possible only if we have a good leaving group. Similarly, why this nucleophile does not attack the or puts its electron into the antibonding of chlorine? If someone asks you why we are attacking it on CS3, why aren't we attacking it on the antibonding of Cl? Attacking means putting its electron. Why nucleophile is not attacking chlorine? Why nucleophile is attacking CS3? If at all nucleophile have to attack this antibonding of chlorine, then the antibonding will the chlorine will start to have a greater amount of electronic wave corresponding to more than 2 electron. So somehow chlorine this time have to empty its electron from the orbital. So what will happen if chlorine empties its orbital? It will go to the orbital of carbon. So nucleophile will have a bonding with chlorine on the completion of this reaction, if it at all occurs, and then Cl minus have to move out, taking the orbital, the electron from the orbital of chlorine. But this CS3 minus cannot move out because this is not stable ion. This is not at all a leaving group. So that's why, since CS3 minus can't go out, so nucleophile cannot attack chlorine. In turn, nucleophile attacks CS3, so that chloride ion moves out. Alright. So that's why antibonding of chlorine atom will not be attacked. Rather, antibonding of CS3 will be attacked, so that CS3 remains intact or form a bond with nucleophile, and Cl minus moves out, leaves the substrate to form a negative ion, because that negative ion will be a stable ion. So considering the stability of the leaving group, we attack the corresponding group, right? So nature of leaving group will be another factor that will determine or govern the rate of reaction of this SN2 mechanism. If the leaving group is very good, then the leaving group will very fast, will show swiftness in moving out. Instead of CS3Cl, if you have CS3Br, then bromine ion is more stable than chloride ion. Bromine ion will be more willing to move out as Br minus. So that will increase the rate of reaction. The resistance shown by Br will be much less than that shown by Cl. If we have CS3I, iodomethane, then the rate of reaction will be yet higher, because iodide ion is yet more stable than bromide ion. So the resistance shown here will be further less than that shown by bromine. So the rate of reaction will increase as you increase the stability of the leaving group. So if leaving group the nature of leaving group is more, if the leaving group becomes more stable, then the rate of reaction increases. So this leaving group, this nucleophile will determine the rate of reaction. Harder the nucleophile, more stable the leaving group, more will be the rate of reaction. Apart from this, you also have an effect of solvent. Solvent. Now solvent is there, we are not drawing it, but these are not dry reagents somewhere in solid or powdered form. They are dissolved in a solvent so that they are free to move and collide and participate in reaction. So that free motion will be there when you have this thing dissolved in a solvent. Either they should be in gaseous state or they move randomly and attack each other, or they should be moving in a solvent. So solvent is there. Solvent is there. So how will solvent affect this? Now we will study some theory here, and that will help to understand the next mechanism. So some part of theory for the next mechanism will be covered here itself. Now there is something called solvation. Now that is done by solvent. Solvent does solvation, and solvation is another factor to be considered here.